Hello, in this video we will talk about how to determine molecular geometries. And so this is the first bit of chapter 8. So the question here is, what is the shape of your molecule? And this is what the molecular geometry refers to. It's the three-dimensional arrangement of atoms in your molecule. We'll start here with just a simple one center and things attached to it, but then you can take these ideas and extend them to components of a larger molecule. And so the thing about molecular geometry that makes it really important is that it affects all of the physical and chemical properties of the molecule. Or maybe not all of them, but many of them. And so this is something that we really want to be able to predict. Fortunately for us, there's a really simple yet really powerful model called the valence shell electron pair repulsion model, which I tend to call this Vsepr because it just sounds easier to say than Vsepr. So what is this model? The easiest way to describe this model is by talking about the letters that make up the acronym. And so valence shell refers to the outermost electron-occupied shell, which we've made a big deal about valence electrons when we're talking about Lewis structures. And so the valence shell is referring to those same electrons. Now, electron pair refers to either a bond or a lone pair. I have a slide on this next that will explain that a little more. And then repulsion is this idea that electrons or bonds or anything containing electrons are negative, and they don't like to be right next to each other because of electrostatic repulsion. Two negatives tend to repel each other. And so the simple idea here is that these electron pairs try to get as far away from each other as they can, and so they spread out around the central atom. And so we'll see a bunch of examples of this in just a minute. So what exactly is an electron pair? So an electron pair could either be a lone pair, a single bond, a double bond, or a triple bond. And what's weird here is that a single, double, or triple bond all count as one pair. And there's a good reason for this that we'll see when we talk about sigma and pi bonds and hybrid orbitals and things like that, but we're not there yet. So for the moment, just roll with it. So for example, over here, this molecule with the sulfur in the middle is called thionyl chloride. That's a non-systematic name, but it's what people tend to call it. And there's 4 electron pairs here. There's a double bond up top, 2 single bonds, and then the lone pair down here. And so electron pair is kind of a crappy word for this. A better phrase is electron group or steric number. And so electron group is a little more generic, right? Something that contains electrons, and hey, bonds are just shared electrons. Or steric number talks about the number of atoms and lone pairs around the central atom, which is the same thing as the number of electron pairs. And steric relates to the physical arrangement of atoms in space. It's a word that we use kind of more broadly. And so steric number is a good word to use for this. Ultimately, the bottom bullet point, I simplify this by saying count the number of things that are hanging off the central atom. On thionyl chloride up here, you got 3 atoms hanging off of it and a lone pair hanging off of it. And the fact that the oxygen up here is double bound doesn't matter. So there's 4 things hanging off this atom. I think that's a lot simpler. Okay, so once you've counted your electron pairs, you go about determining the molecular geometry and the electronic geometry by doing this. So first up, you have to know what you're looking at, so you draw the Lewis structure first. Then you have to count the electron pairs, which we just talked about. And then you have to arrange them to minimize repulsions. And how you do that, well, really you just see how many of them there are, and then you learn what the shapes are that minimize repulsions for that number of electron groups. We only have 5 of them, 2 through 6, and so it's pretty easy to learn what these shapes look like. Then you name something called the electronic geometry from the position of all electron pairs. This includes lone pairs. You'll need to memorize what these names are, and I'll talk about this in detail in the next slide. Forecasting forward, you then figure out which ones of your electron pairs are atoms, and then you name something called the molecular geometry only from the positions of the atoms, not including lone pairs. And we'll get back to this in a minute. But let's talk about electronic geometry first. So like I said, there's only so many choices here. your central atom can be bound to one other thing, in which case geometry doesn't make sense because it's just a line, two things bound together. Your central atom can be bound to two other things, 3, 4, 5, or 6. It is possible to have 7. I don't go into that in Gen Chem, and it's pretty darn hard to have 8 or 9. I'm sure these exceptions exist, but it's generally not the thing. Okay, so if there's 2 things hanging off your central atom, we call it linear. That makes sense because it's in a line. If there's 3 things, we call this trigonal planar because there's 3 of them, tri, and because it's a plane, planar. If there's 4 of them, we call it tetrahedral, and that's because if you shrink wrap this thing, it looks like a tetrahedron, and we'll get to that in a minute. If there's 5 of them, you call it trigonal bipyramidal because there's 2 pyramids that have a triangular base, and again, I'll show this in a minute. And if there's 6 of them, you call it octahedral. So let me show you what this looks like. And so if we're going to do linear, all right, I can go here, I can hit Vsepr, I can just show an example of something linear. Hey, look, that's a straight line. If I kind of rotate it this way, you can see that it really is just 3 atoms in a straight line. This one's showing an example of CO2. But for any linear molecule, hopefully it's fairly obvious that the reason this geometry is linear is because it allows the electron groups to get as far away from each other as possible while still being bound to the central atom. Now, if we move on to the trigonal planar one, there's 3 atoms connected to the central atom, and they're in a plane, and so you can rotate them and see the plane right here and spin it like, hey, look, this is all in the same plane. And then since there's 3 of them, it's trigonal. So I can rotate this back up and say, hey, look, there's 3 of them here. Now, if there's 4 of them, we call this tetrahedral. And so here's what that shape looks like in the molecular model version. And this is named after a tetrahedron, which is this shape. So a tetrahedron is a geometrical shape that has 4 sides and 4 triangular sides, and that's called a tetrahedron. And so if you park the central atom in the middle of the volume of this tetrahedron, the exterior atoms are the corners of the outsides of this. So the way I say that is that if you shrink wrap this tetrahedral molecule, you'll have 4 faces. And then the central atom will be hanging out in the middle. And so that's tetrahedral. All right, moving on. So if you have 5 of them, it's trigonal bipyramidal, and that looks something like this. And so this is also named after a geometrical shape. So the trigonal bipyramid looks like this. It's 6 sides. It has a triangular middle and then 2 pyramids on top, or a pyramid on top and a pyramid on bottom. That's what that looks like. And again, if you shrink wrap something that's trigonal bipyramidal, it will look like that. It'll have 6 faces, and the central atom will be kind of in the middle. So this has 2 non-equivalent positions. So these ones up top and bottom are called axial. See, these ones are axial right here and right there. And then the ones along this middle are called equatorial, because it's like you have a little planet. Whoa, little planet, big planet. It's like you have a planet, and these 3 in the middle are on the equator, and then the top 2 in the bottom are the axis around which it spins. So if I rotate this down like that, then we now see the axis going left to right, the axis coming front and back, left to right, front and back. All right, so spinning it with the axis pointing towards you looks a lot different than, let me see if I can get this back up here, spinning it with the axis up and down. So that's what that shape looks like. And moving on to the last one, we have octahedral. The octahedral one looks something like this. And now it's mislabeled in this website as trigonal bipyramidal. This is actually the octahedral one here. And again, this is named after a shape called an octahedron, which has 8 triangular sides. And if you shrink wrapped the trigonal bipyramidal molecule, which has 6 things bound to it, it would have 8 faces. And so that's why it's called octahedral. And here, there's no axis, there's no equator. They're all the same. I can rotate this 90 degrees towards us, and then spin it and it'll look pretty much the same. Right, I can rotate this 90 degrees like so. You can rotate it any direction 90 degrees and it'll look the same as it did before. It's a very symmetrical shape. And so that's the octahedral. Again, it can be a little confusing because there's only 6 ligands, 6 things bound to the central atom, but it's octa is the root word here. Because there's 8 faces if you shrink wrap it, but only 6 atoms around the central atom. Okay, now that we've talked about electronic geometry, now is a good time to take a break if you need one before we continue and talk about molecular geometry. So now let's go back to the slideshow and keep moving. So we just named the electronic geometry. That's number 3 on this list. And you call that based off of all the things attached to the central atom, whether they're atoms or lone pairs or whatnot. Now we have another name called the molecular geometry, where we name this just from the positions of the atoms. And there's a few more names to memorize. Now, if your molecule has no lone pairs, then your electronic and molecular geometries are the same. It's when you have lone pairs that it starts to mess things up. So let's talk about these in order. So if you have 2 electron pairs around the central atom, we call this electronic geometry linear, which we just showed. And really, that's your option here. There's no way to put lone pairs on this and still have geometry make sense. So I'm going to show a table here. It has electron groups, and then it has the numbers of atoms and lone pairs that make up those electron groups. So atoms plus lone pairs equals number of electron groups. Then it's got my little diagram for the shape, and it talks about the bond angle. That's also something we need to know. And then it gives the name of the molecular geometry. So here, since there are no lone pairs on the central atom, that means that our molecular geometry and our electronic geometry are the same. They're both linear. And beryllium chloride is an example of this. Now, when you have 3 electron pairs around your central atom, you have trigonal planar electronic geometry. And this is what we showed. We showed it as if there were 3 atoms around it, because it's easier to make a little model like that. But, okay, so you have 3 electron groups, and now you can either have 0 or 1 lone pairs. And remember, we're only considering the lone pairs on the central atom. Only on the central atom. And so, all right, now we have 2 choices. So if you have no lone pairs, the molecular geometry matches the electronic geometry, same name. And this bond angle here is 120 degrees. Now, when you have a lone pair here, here's our lone pair, this little thing right there. Now here we call this bent, because this molecule looks kind of bent. And this bond angle here should be about 120 degrees, because remember the one up here is 120 degrees. But it's not quite 120 degrees. It's a little less than 120 degrees, because this lone pair exerts more of an influence on the bonds around it than the atoms do in the one above. So because there's a lone pair, it tends to push these bonds down a little more, and then it reduces this angle and now makes it less than 120. That looks like kind of a smiling clown. That's kind of cute, actually. Yeah. Okay, so some examples here. Boron trifluoride is trigonal planar. All right, this is because boron can have a deficient octet, so it doesn't need a lone pair on the central atom, and so then that makes this Lewis structure work out. Now, sulfur dioxide is an example of something that can exceed its octet, and its best Lewis structure is like this, and it has 2 atoms and a lone pair on it, which makes 3 electron groups, and one of those is a lone pair, and so that makes this bond angle a little less than 120. In this case, it's 119. But all you need to know is that this bond angle is less than 120. That's all you need. Now we can show this on our geometry shower, right? This is the trigonal planar that I showed before. And then if we take one of these out and put a lone pair on it, so with the lone pair, you would call this trigonal planar because there's 3 things on this central atom. But when you name the molecular geometry, you consider it without the lone pair. And you look at just where the atoms are. So this thing is bent. Now, moving on, when you have 4 electron pairs around your central atom, you have tetrahedral electronic geometry, and now you have your choice of 0, 1, or 2 lone pairs. And the names we associate with this is tetrahedral. There's no lone pairs, you have the same electronic and molecular geometry. Or trigonal pyramidal if there's 1 lone pair, and then bent if there's 2 lone pairs. And again, the bond angles change. And so we're looking at this bond angle right here. Well, really all the bond angles are the same. They're all 109.5. Now, if you put a lone pair here, it's a little bigger. It exerts more of a Vsepr effect, more of a repulsion. And so that makes these bond angles a little less. In the case of ammonia, it comes out to be 107 something. And so then when you have 2 lone pairs here, they exert even more of a repulsion, and then this bond is even smaller, about 104.5. And so that's the case when you have bent. Notice we have bent twice. There's the 120 degree bent and the 109.5 degree bent. Well, really less than 120 and less than 109.5. And that just depends on how many lone pairs you have. 2 lone pairs, tetrahedral electronic geometry, still bent. 1 lone pair, trigonal planar electronic geometry, still bent. All right, here's some examples. Let me show this. So let me do the tetrahedral one first. And so we've been using this molecule to show off tetrahedral. I already showed that. Now, if we switch to this molecule, this is ammonia, if you include this kind of blobby electron thing, there's 4 groups, and we call that tetrahedral when you include the electrons. But when you don't include the lone pair, we call this trigonal pyramidal. And these 3 white atoms are, say if they are sitting on a table, they will sit on the table. And then your blue atom in the middle will sit up a little bit off of the center. And so this makes a pyramid. It's a pyramid with a trigonal base because there's only 3 atoms. And so it's called trigonal pyramidal. All right. So now the next one is bent. And it just looks bent. Like it just looks kind of like that. Hopefully that's pretty self-explanatory as to how that looks. All right, again, with the lone pairs, it has a tetrahedral electronic geometry. And when you take the lone pairs away to name the molecular geometry, then it's bent. So there's only 2 things here. All right, so in these examples, we're modeled off of methane, ammonia, and water. Okay, so now we need to get to this, how to represent 3-dimensional molecules on a flat surface. And please remind me to talk about this in class, and I'll show it on the board a lot better than I can do on a screen. And that said, the idea here is that put as many atoms as you can in the plane of the page. So here, these 2 atoms are in the plane of the page. And then this one is coming out towards you. And then this one's going back into the plane of the page. And so this wedge is trying to show perspective of, it's coming out towards you. Imagine this line is the same thickness all the way along, just that when it gets closer to you, it looks bigger. And then this dashed one just means it's going away from you. And so it's trying to show this, where you have the top and the left atom in the plane of the page. And then this one here comes towards you that I'm grabbing with the mouse. And this one here is away from you in the back. So that's what that's trying to show. Okay, moving on. 5 electron pairs. Feel free to take a break now and come back if you need a little rest. All right, so 5 electron pairs. Now there's more options. You can have 0, 1, 2, or 3 lone pairs around this central atom, and there's a different name for each. So like we saw before, if there's 0 lone pairs, your molecular geometry and electronic geometry are the same, trigonal bipyramidal. And your bond angles here, there's 2 different types. From the axial to the equatorial is 90. And then between the equatorial positions is 120. And so you have to remember both of these, and you have to list both of these because they are different. You got to include both of them. Now, when you have a lone pair, so here's your lone pair, right? You name the electronic geometry as if this lone pair counted, and so that's trigonal bipyramidal. But you'll name the molecular geometry as if that didn't count. And we call this a seesaw, or sometimes distorted tetrahedron. And so the bond angle between here and here is a little less than 90. And then the bond angle between the equatorial positions is a little less than 120, that one. Because again, this lone pair exerts more influence and tends to push these other atoms closer together. So this is called a seesaw because if you put the ground right here, it'll look kind of like a seesaw. So let me just show that. So here's the seesaw as we see on the screen. And now if I rotate it such that two of these are on the ground, I wonder if I can do this. This will look kind of like a seesaw, where you might put the kids right here, and then they bounce up and down this way. So that's why it's called a seesaw. Okay, kind of a cute name. And yeah, this is the shape it has. Trigonal bipyramidal with a hole in it, if you will. And so we call that seesaw. So you may be wondering, why are the lone pairs in the seesaw shape, why are they here in the equator and not on the axis? And well, that's a good question. Let's think about that. And so this is definitely true. The lone pair occupies an equatorial position and not an axial position. And the reason for that is because of repulsions. And so in the axial case, if you put the lone pair in the axis here, then it has 3 lone pair bonding pair repulsions. So that means that this stronger repulsion between the lone pair and these 3 fluorine atoms, well, there's 3 of them. Whereas if you put the lone pair here, then there are only 2 repulsions between this lone pair and atoms that are 90 degrees apart from them. Sure, you gain a couple more repulsions to atoms that are 120 degrees away when you put the lone pair in the equator, but that's overall better because there's less of these stronger repulsions between the lone pair and the atoms 90 degrees away. So because of that, when you put 1, 2, or 3 lone pairs into this trigonal bipyramidal shape, they all go in the equator because that minimizes repulsions to atoms that are 90 degrees away. Okay, moving on. And so T-shape looks like this, and if you spin it, well, you'll see that it is named because it actually kind of looks like a T. That's pretty straightforward. And so in the T-shape geometry, you still have the 2 axial positions, then only 1 equatorial position. Like we just said, for all of the trigonal bipyramidal geometries, the lone pairs go in the equatorial positions. Now let's move on. Let's do the linear one. And hey, it's a straight line. That's pretty straightforward. But again, the lone pairs go here. Whoop. And so if you include the lone pairs, and they're 3 different colors because there's 3 different lone pairs here, then that makes the electronic geometry trigonal bipyramidal, even though the molecular geometry is linear. So here are some examples. PCl5 is trigonal bipyramidal, ClF3 is T-shaped, and the triiodide anion is linear. All right, here's another quick spot for a break if you want one. And I'm going to carry on and talk about the 6 version. For octahedral geometry, we really only consider when you have 0, 1, or 2 lone pairs, because the case where you have 3 or more lone pairs doesn't really happen that often. And now this name is octahedral, because the octahedral electronic geometry, and if you have all atoms there, that the molecular geometry is octahedral. And this bond angle here is 90 degrees. Now, when you put a lone pair on it, it doesn't matter where that lone pair goes because all of these sites are equivalent. There's no axial or equatorial. And so I just parked it on the bottom because it looked pretty. And so that, again, takes up a little more space. And so this angle here is a little less than 90. And this is called square pyramidal because this is a square base and it makes a pyramid if you shrink wrap it. So that's why that's called square pyramidal. And then if you keep going, well, to put 2 lone pairs on here, now the place matters, and you put them across from each other so they don't get in each other's way. And so you park the lone pairs across from each other, that leaves you these 4 atoms in a square. Okay, so now let me show this with the magic geometry thing. And so here's the octahedral shape. I already showed this. Again, all of these positions are equivalent. And now if we go to square pyramidal, I'll rearrange this so it points down. There's the lone pair. And so again, with the lone pair, you call the electronic geometry octahedral. Without it, you call the molecular geometry square pyramidal. And again, it's like a square, And then if you shrink wrap it, it makes a pyramid, and it's a square pyramid. So that's what that looks like. All right, then if you go one more lone pair, this is square planar, and so here are the lone pairs. And so one goes up, one goes down so that they don't get in each other's way. And this makes a plane, and so that's why this is called square planar. And so when you name it by just the atoms, the molecular geometry, it's called square planar. Makes a square. There you go. And so here are some examples. SF6 is octahedral, BR5 is square pyramidal, XeF4 xenon tetrafluoride is square planar. And again, the same thing happens with the bond angles. It gets a little smaller when you put the lone pair on there for BRF5. But for xenon tetrafluoride, these bond angles are back to 90 degrees because the action of the two lone pairs counteract each other and keep the bond angles all 90 degrees. Okay, and so to summarize this, on Moodle I have a handout that looks a little something like this. And so on this handout, let me point out a couple things. Each one of these big bold boxes is a separate electronic geometry. And so if you'll notice here, okay, the electronic geometry for both of these is trigonal planar. And if you have a lone pair, then you call the molecular geometry something else, right? The names in this sheet are all molecular geometries. Now, the very last thing I want to point out is this far right column called hybridization. And this is something that you're going to learn later, but hybridization depends only on the electronic geometry. So notice that the hybridization is the same for all of these because they all have the same electronic geometry, the same 4 electron pairs. All right, that's what I have. Thanks for watching.